Okay, so I'm going to take a look at how to graph quadratics from vertex form. In class, one of the things we talked about is how to graph a quadratic from standard form. So this is just a quadratic function given in standard form, something ax squared plus bx plus c. And you see I've got numbers in there. And of course, if I wanted to graph this, one of the ways I can always graph a function is just by plugging in different x's. Now we could just randomly plug in values like 0, 1, -1, and see what happens. But one of the things we did talk about is the axis of symmetry for a quadratic in standard form is given by x equals -b over 2a. So looking at this right here, I can see that b is 6, and I can see that a is 1. So if I go ahead and do this, -6 divided by 2 is -3. And if I wanted to find the vertex, I can then take that -3 and substitute it to find the y-coordinate. And if I do that, I now have -9 plus 4, which is -5. All right, so I can see my vertex is at -3, -5. I can go ahead and plot that on my grid right here. There's -3, -5. Now, of course, 1 point is never going to be sufficient. Generally speaking, you need around 5 points. More, if you can get them, is really better. Can make a little table here. I'll put my vertex right in the middle. And what I want to do is pick some x's a little above and a little below that. And again, one of the things we said we can do is just substitute and go directly at this. So I can worry about what happens if x is -2. Well, if x is -2, then I have y is equal to -2 squared plus 6 times -2 plus 4, which is -4. If x is -1, I can substitute, and that will give me 1 minus 6 plus 4, which is -1. So I've got these points now, 2, -4, -1, -1. And I could keep going. Like if I put in 0, I can figure out pretty easily I'll get 0, 4. But the idea is a parabola is symmetric. It's symmetric about the vertical line through the vertex, the axis of symmetry. So where I have -2, -4, I would also have -4, -4. -1, -1 means I would also have -5, -1. So I can reflect these over here. I need that symmetry. And I'll even use the 4 that I have up here. Okay. Now once I have these points, I connect them as best as I possibly can with a smooth curve. Nice parabola that gently opens as I go further and further up. Try and make it approximately smooth. And we can analyze that. We can find the axis of symmetry we already have, the vertex. We can do all that. Now this is a decent enough way to graph a quadratic, but truth is there's actually a better way to do this. A more efficient way is to consider what is called the parent function and transformations. The parent function for a function family is the simplest possible version of a function. So like for a line, I might have y equals x. And we'll have other parent functions as we talk about more functions throughout the year. The quadratic parent function is the simplest quadratic, which is y equals x squared. So I can make a little table right here of x and y, which is x squared, and I'm going to come up with some points. I'm going to go from -3 to positive 3. And I want to think about what happens if I square each of these things. I'm going to start in the middle. If I square 0, I get 0. If I square 1, I get 1. 2 will give me 4, and 3 gives me 9. Now if I go into the negatives, if I square negative 1, I still get positive 1. Negative 2 will also give me positive 4, and negative 3 gives me positive 9. So let's take a look at what this looks like on my grid. Here's 0, 0. The origin is my vertex. I have 1, 1, but I also have negative 1, 1. I have 2, 4, and I also have negative 2, 4. And I have 3, 9, as well as negative 3, 9. Again, I see that nice symmetry. But more than that, more than the symmetry, I have a nice little pattern here that I'm going to be able to use to graph. You notice all these points are arranged in a particular way. As I go out from my vertex, I can go out 1 and up 1 on both sides. I can go out 2 and up 4 on both sides from the vertex. And I can also keep going. I can go back to the vertex. I can go out 3 and up 9. So this will give me a pattern that allows me to graph a parabola very effectively, much the same way as I would graph a line using slope. Now, if we think about this, this is a parent function. I said we're also going to introduce things called transformations. How would the graphs of these functions compare to the parent? Well, if I said y equals negative x squared, well, if I took all of these outputs, if I took 0 and 1 and 4 and 9, and I put a negative in front of them, then what would happen is all these points would come down below the x-axis. So the points go down, or in other words, for example, negative 2, 4 would go to negative 2, negative 4. Negative 1, 1 would go to negative 1, 1, and so on. So what I'm going to get here, how I would describe this as a transformation, I'm going to say that the graph is going to be reflected downwards. It's reflected across or in the x-axis. What if I said x squared plus 5? Well, x squared plus 5, I have to imagine I do the same math I would up here. I would square 0 and get 0, but then I would add 5. I'd square 1 and get 1, but then I would add 5. Square 2 and get 4, but then I would add 5. So each of these points is going to be 5 units higher in the plane. Well, that seems pretty easy. This seems like what's going to happen is I will shift the graph and all those points up 5 units. All right, now if I say x plus 2 squared, you might think, and it would make sense, well, this moved me up. If I did minus 5, it probably makes sense that what's going to happen is the graph will go down. So you see this plus 2, and you might be thinking, well, that's probably going to move the graph left or right. But which way will it move it? Your brain probably sees plus 2, and you immediately want to think, oh, it's going to move it to the right. Well, let's think for a second. When x is negative 2, I will have negative 2 plus 2 squared. That's 0 squared, so that's 0. If x is negative 1, I will have negative 1 plus 2 squared, which is 1 squared, which is 1. If x equals 0, I would have 0 plus 2 squared, which is 2 squared, or 4. And I could do this for any number of points. What does this look like on the graph? Well, I now go through negative 2, 0, and I go through negative 1, 1, and I go through 0, 4. And I could fill this in. I would have the rest of the points. If I put in negative 3 plus 2 is negative 1. I square that and I get 1. And I'll get something similar. I'll still have that symmetry. And I can see that even though I saw that plus 2 and immediately wanted to say, oh, I'm going 2 to the right, what actually happens is I have gone 2 to the left. Now, of course, you can confirm all of this stuff using something like a graphing calculator or Desmos, but these are some ideas that we're going to play with a lot. We want to be able to identify how putting in certain numbers changes the graph. And that idea is what's called a transformation. So, we'll talk about the vertex form of a quadratic and transformations. This is the vertex form of a quadratic. I know it's a quadratic because of this square. This form of this function allows us to identify transformations very easily. A transformation is a change to a function's equation, and then by consequence, its graph. Each of these little numbers, if they're not 0, will represent some sort of transformation. The first thing we saw, if I put a negative out in front here, it reflected the graph in the x-axis. So I will reflect in the x-axis if a is less than 1. I will stretch or compress the graph vertically, so I will make it go up faster or slower, depending still on a, but not a's sign, just its magnitude. I said a is less than 1. I apologize here. I meant a is less than 0. So for example here, if I said something like y is equal to negative 3x squared, the negative means I reflect in the x-axis. The 3 means I have a vertical stretch. These make more sense when you see them in action. Now, the big thing right here, this is called vertex form. It's called vertex form because it gives us the vertex. Notice I have minus h and plus k. Very important that that's minus and that's plus. My vertex is h and k. So if I wish to translate this graph, the vertex right here represents a translation. The parent function goes through the origin. The vertex translates the graph by h and k units in some direction. I will translate left or right based on h. I will translate up or down based on k. Here's the thing. Like we saw in the previous example, when we saw x plus 2 squared, that actually moved us to the left. So with h, you have to think about it's an opposite sign. So if I saw something like x minus 3 squared, then even though you see minus 3 and might think 3 to the left, I actually want to think about plus 3, which would mean 3 to the right. K, this number that I add at the end, will be a normal sign. So if I see y equals x squared minus 7 means I will go down 7 units. Those translations tell me where my vertex is going to go. So once we grasp these ideas, this will be the most effective way of graphing a quadratic. So let's take a look at some examples. I want to transform the parent function to graph each function, and then I want to give the vertex of each function. So what I'm going to do is look at each of these equations. So I know what my parent function is. I'm going to make a note of what my parent function is. The points of y equals x squared are here. I'll go ahead and plot these. And I'll even put a little dashed curve through them. Not solid, because this is not the function that I'm graphing. Now I see here I've got x minus 3 squared and I've got plus 1. So I'm going to start thinking about those transformations. I know whatever's inside is going to move me left or right, and whatever's outside will move me up or down. So that minus 3 means I will go 3 to the right, because I know I need the opposite sign, and plus 1 means I will go 1 up. So I can move my vertex 3 to the right and 1 up. And again, space these points out. I can move these points individually. 3 to the right and 1 up. 3 to the right and 1 up. And keep doing that. Nice smooth parabola through there. That's the function that I want to graph. With a vertex at 3, 1. Okay. Let's take a look at another one. Y equals negative x squared plus 4. So I look at the transformations here. I know this negative means I will reflect. I know this 4 means I'm going to go up 4 units. But when I think about this, again, I want to think about my parent function. So my parent function would go through these points. This right here is reflected. So I'm going to make another column right here to indicate my reflection. 4 will become negative 4. 1 becomes negative 1. 0 will stay 0, but I can change the signs on all these other ones. I don't need this column anymore. So now, what I have are the points 0, 0. I now have 1 and negative 1 down at negative 1. I have 2, negative 4, and I have negative 2, negative 4. That's my parent with a reflection. Now the question is, what am I going to do with these points? I see this plus 4 right here. What that means is I'm going to take each of these points and go up 4 units. So I see here where I previously went out 1 to either side and down 1. I'm still going to do that. where I previously went out 2 to either side of the vertex and went down 4, I'll still do that. And I could get more points if I wanted to. But just a general idea of what I'm doing here. That's my function right there. Its vertex is at 0, 4. And it's opening down because there is a reflection. Do one more example of a graph. Here, I see y equals 2 times x plus 2 squared minus 5. So I want to think about what are the transformations here. I know this 2 right here means I will go 2 to the left. I know the minus 5 means I will go 5 down. And this 2 out in front means I will also stretch vertically. Okay, so I'm going to do this a little bit differently. I could graph the parent function, but this stuff essentially tells me how to work with this. If I'm going 2 to the left and 5 down, I'm moving from the origin to my vertex. I go 2 left and 5 down, and that puts me at my vertex. -2, -5. Okay. Originally, the way I spaced my points out whoops, not 4, 2. Is like this. Now when I did the reflection in the previous example, I multiplied all these by a negative. Here, I have a stretch, so I'm going to multiply all of these by 2. So I have two options. I could plot these points and then shift them individually 2 to the left and 5 down. Or I could be a bit more clever about this. Here's my vertex. What this is really telling me to do is from my vertex to go out 1 to either side and up 2 units. It's also telling me from my vertex to go out 2 to either side and up 8 units. So I'll do that. Out 2 and up 1, 2, 3, 4, 5, 6, 7, 8. And then as best I can, I'm going to put a nice smooth parabola through these points. So those are the points I would get if I took my quadratic, I shifted it 2 to the left and 5 down, and stretched vertically by a factor of 2. Couple more examples. Let's just look at some equations and see if we can identify the transformations. Right here, f of x is equal to -3 times x minus 6 squared. So when you look at this and you're analyzing for transformations, you should see 3 things. There's a negative, there's this 3 out front, and inside I'm subtracting 6. The negative means I will reflect in the x-axis. The 3 Well, 3 is greater than 1, which means I have a vertical stretch. By 3. I see x minus 6 inside. I remind myself that every time I'm inside, the sign works opposite of how I would think, which means I'm going to shift or translate 6 units in the x direction, in the positive x direction, so 6 units right. One more over here. H of x equals 1/2 times x plus 1 squared minus 1. This 1/2, since 1/2 is less than 1, what I have here is a vertical compression. Which would mean rather than rising faster, it'll rise a bit slower. I see plus 1 inside, which means I will shift 1 to the left. And I see minus 1 outside, which means I will also shift 1 unit down. So this gives us a basic idea of how to work with transformations of quadratic functions.